Good evening, this is N7GES, and welcome to the NCARC Tech Net. We meet each week on this at this time to discuss technical topics or other topics involving amateur radio. You can hear us on this machine, the 447-275, the 447-750, on Echolink at W0UPS-R, and we're also streaming to YouTube, so you can listen there or receive our previous broadcasts, net broadcasts as well. If you have suggestions for the net or topics you'd like to see discussed, please email us at elmers@ncarc.net. That's Elmers as in the person's name, elmers@ncarc.net. Let's see who is here tonight, and just for the purposes of finding out who's listening. N7GES, who's willing to check in this evening?
Net Control, W0GWC.
Kilo Alpha 6, Echo Tango Echo, Jim in Loveland.
Kilo Echo 0, Tango Mike Delta, Ryan in Loveland.
And 0EMP, Greg, Fort Collins, with Debbie, K0DBE.
KE0OXV, Scott in Fort Collins. Alpha Echo 0, Charlie Foxtrot, Ben, Fort Collins.
Okay. Good first set of check-ins here. AE0CF, KE0OXV, K0DBE, N0EMP, KE0TMD, KA6ETE, and W0GWC. Welcome and good evening. Who else is out here?
W0SMC, Whiskey 0 Sierra Mike Charlie, Sandy from Nunn.
All right. Welcome, Sandy, W0SMC. Welcome and glad to have you. Anybody else wishing to check in?
Whiskey Yankee 0, Whiskey Yankee Oscar from Cheyenne, just traveling through listening.
Okay, I love that call, WY0WYO. Are you actually from Cheyenne?
Yes, from Cheyenne.
Okay, well, welcome and glad to have you. Thank you very much. Anybody else wish to check in? Okay, well, let's begin with our topic here this evening. was suggested we talk about what part of the dipole does the radiating and why must it be so long? So we've got some interesting things there. Some of you will know about already. Some of us may not. So let's see what answers we can get and what information we can glean here. Anybody like to give that a start here?
Whoops, overrun the wrong machine. W0LEV.
Good evening, Dave, LEV. I understand how that goes. Yeah, good evening, and would you like to get us started here?
Well, I'll try. I missed the beep there. I'll throw out another question, because it's highly apropos. Somebody tell me what resonance represents.
EMP.
Answer.
Okay, we had EMP just before you jump back, Dave. Go ahead.
I can kind of address all three of these things together, and talking a little bit about each one, hopefully all the pieces will come together and make sense.
Go ahead, please.
Can we give the newbies a stab at resonance first? I'd like to draw out a little bit of what they might have learned on their exams.
Okay. Do we have any folks that are fairly new that would like to give that a shot, specifically resonance?
Again, silence is not a good answer. They should have been alluded to on some of the exams you took. Okay, I'll cede the answer. Inductance and capacitance. Think about it.
Okay.
Greg, go ahead. I give up. W0LEV.
Go ahead, Greg. EMP.
Yeah.
Okay, I'm going to talk about these things in no particular order, and at first you might think, where am I going with this? But trust me, I think it'll all come together at the end. So we'll start with resonance. If me and our club president, Joe, KD0TYU, go down to the park, and Joe starts tugging on my sleeve and says, Greg, push me on the swing, push me on the swing. Joe can get on the swing, and I can start pushing him, and he's going back and forth. Now, if you know me and you know Joe, he's a little bigger than I am. But if I time my pushes, so I step in and push as he's swinging away from me, and then I back out of the way as he swings back towards me, everything is fine. And after a little bit of not pushing very hard, really, I can get him swinging up real high, back and forth. That's resonance. Let me reset this. Now, if I get my timing wrong after I've got him swinging back and forth really good, and I step in to push him just as he's at the bottom of his swing coming back into me, that's a non-resonant condition, and I'm going to get knocked back onto my fourth point of contact. And that you might think of as high SWR. I just got a big kick back and knocked down. So the rate at which he swings back and forth is his frequency on the swing. And if my pushes are in phase with his frequency of his swing, everything's good. So that's resonance. Now a few concepts. RF energy, radio frequency energy, is alternating current. That means the polarity switches back and forth. And if we're talking here on this repeater, what you're listening to is switching back and forth 447.275 million times a second. It's changing polarity. And when electricity changes polarity, it changes direction. The current that's flowing as a result changes direction. Now we're going to jump to a dipole antenna, which is one of the simplest antennas out there. Half wavelength long. That means each half is a quarter wavelength long and fed in the center, fed in the middle. We'll keep it all very simple. When you hook RF to that feed point at the center, current starts flowing down one leg, and when it gets to the end, it's got nowhere to go. It reflects back and comes back towards the feed point. As your polarity reverses of your RF energy, current starts going down the other leg and then comes back. And in actuality, current's flowing in both legs, through both halves of the cycle. It's flowing in one leg and out the other, back and forth. Think of the same thing as the swing. Swinging back and forth on the swing. And the dipole, you've got current swinging back and forth on the dipole. The current going down the dipole goes at a certain speed, almost the speed of light, very slightly less because of different physics effects and whether or not there's insulation on the wire or not, so almost the speed of light. So it's going at a certain speed, and it reverses direction a certain number of times a second based on your frequency. All that works out to where if you have quarter wave lengths of your two legs of your dipole, the timing all works out fine, so from cycle to cycle to cycle, it's all in phase. That power is going down the wire, it hits the end, it reflects back towards the feed point, and it gets there just in time for its next push the other direction down the other leg and back. So it's the same as pushing someone on the swing at the right rate or right number of times per minute or whatever you want to count it as, to where everything is in phase. So because of the speed at which the current goes down the wire, and because of how long you want the wire to be, a quarter wavelength, and because of the frequency you're transmitting on, that's why a dipole is the size it is. And that's why as you go higher in frequency, the dipole gets shorter. Let me catch my breath here in 0 EMP.
Yeah, comment when you're done, Greg.
Almost there. Let me get into the actual transmission of a radio wave. What is a radio wave? Well, it's an alternating electrical field and an alternating magnetic field. There's two things that are important to know. An alternating electric field creates an alternating magnetic field, and an alternating magnetic field creates an alternating electrical field. This is how a transformer works. We have two separate windings on a core, and they're not electrically connected, but they're magnetically coupled. And you put AC in one end, and you get AC out the other end. If it wasn't for this fact, radio waves would not propagate the way they do. We'd still have near-field effects, and you could talk to someone a few wavelengths away from you through induction, but you wouldn't be transmitting across the state or across the country or across half the globe. So once you get this electromagnetic field launched out into space and it's propagating, the energy in that RF wave is switching back and forth between electric and magnetic. And they're at right angles to each other, and they're at right angles to the direction the wave is traveling. So it wasn't for those two pieces of physics, these waves wouldn't even propagate. The purpose of a transmitting antenna is to get the ball rolling in the first place. And I'll reset this. So current, alternating current flowing through a single wire in space radiates that alternating magnetic field, which in turn generates an alternating electric field, then a magnetic, then an electric, back and forth as it radiates away from the antenna. So current is what a lot of people, including me, will argue is what causes an antenna to radiate. Now, if you have two wires parallel to each other with equal and opposite currents, like in a piece of ladder line or twin lead feed line, the fields cancel each other out because they're opposite of each other. That's why twin lead or ladder line or window line, it's sometimes called, can be used as feed line without radiating if the two currents are equal and opposite. But a single wire out there with current alternating in it radiates. Last piece about dipoles, and then I'm all done. Let me reset this. In the dipoles that we've described, half wavelength long, fed in the center, resonant, near the feed point, it's a lot of current and low voltage. That's where the radiation is occurring. As you go out towards the end, you get less and less current flow in that section of the wire. The voltage starts piling up, and you get higher and higher voltage. If you're going to get an RF burn off a dipole, it's going to be out at the end where you have high voltage, and you can get a burn off of it. So the part that radiates is closer to the feed point, like the first third, first half is where the bulk of your actual radiation of RF is occurring at. Because of that, you can fold that last third of your dipole, last third of each leg, you can fold it up to 90 degrees without really affecting the performance of the antenna. If you're trying to put in an 80-meter dipole and you don't have room, you can fold that last third down towards the ground. Let's say you had a horizontal dipole. You could fold that last third down towards the ground and do just fine. You don't want to bend it over 90 degrees. Let me reset this. And you don't want that end that you folded down to get low enough that someone can touch it and get an RF burn off of it. Plus, if you get it close to the ground, you start affecting the resonance, and then you got to retune it by cutting some off. But some of you guys have worked with Moxon antennas, and that's just a Yagi, which is a driven dipole and then a reflector dipole behind it. And the last third, approximately, of the driven is folded back, and the last third of the reflector is folded forward. And that's why you can do that, because the real radiation's occurring in the first two-thirds or so of the antenna. So that last bit is just time delay to make everything be in phase from cycle to cycle. And 0 EMP.
Okay. Thank you very much. Dave, go ahead, please. This is N7GES with the TechNet.
W0LEV. Yeah, Greg covered what I was going to mention about the center is low impedance, high current. The ends of the dipole are high impedance, high voltage. And if you look at that, it's just Ohm's law. You don't need to use complex algebra or vectors or tensors to realize that. It's just simple Ohm's law. But realize, again, Greg stated it, but it needs to be driven in. It's the high current portion of the antenna that produces radiation. And you ask, why do I even need the rest? Well, high impedance, low current, or high voltage is at the end of it. That's the capacitive part, which doesn't really shake the ether. The high current portion, that's inductive-ish. That's moving lots of current. That's what does the radiating. And you can look at the center of a dipole as being inductively dictated, but it requires the capacitance at the end, that is to make it long, to become resonant. So resonant dipole oscillates between the two halves, inductive, capacitive, capacitive, inductive, and you can actually pretty well model a lumped behavior using lumped elements. Of course, they don't radiate. That's enough for me, W0LEV.
All right. Hopefully we've put out enough info there to generate perhaps some questions. Any questions about all this? This is interesting and important stuff, especially if you're making your own antennas, to understand what's going on here. So, any questions about all this?
MIC.
Good evening, Mark. Go ahead.
May we please talk about screwdriver antennas and coil-loaded antennas and capacitance hats, W2MIC.
Okay. Anybody want to give that one a try here?
EMP.
Or inductively loaded antennas. It can be proven from basic principles, that is Mr. Maxwell's famous 4, that you can shorten a resonant radiating structure by as much as down to 10% without losing efficiency, all other things being equal. The devil's in the details, theoretically. So what happens in a screwdriver, a quarter wave on 40 meters is nominally about 33 feet. But a screwdriver resonated on 40 meters nowhere near 33 feet. The inductor makes up the electrical delay that the distributed wire would otherwise accomplish in coupling to free space. The price paid, of course, is bandwidth. The screwdriver bandwidth, 2-to-1 swerve points, is much, much closer than the 2-to-1 swerve point of a dipole in free space. What the capacitive hat does is, again, what's the reason for the end of the dipole being so long? Capacitance, so it can resonate against the inductance. The capacity hat adds capacitance, so there's more current drawn up farther, through the coil and up farther on the radiating structure, so you get more efficient radiation and also a higher radiation resistance. W0LEV.
Okay. EMP, did you have more to add to that?
I did, Kevin. Another way to look at it is time delay. With the simple dipole, that's a quarter wavelength on each leg, there is a amount of time that it takes the RF to go down to the end of the wire, build up charge, and reflect back towards the center feed point. You can shorten things by putting a coil somewhere in the middle, which takes some time for the RF to wiggle through, or you can put what's called a capacitance hat on the end, which can just be some wires sticking off at 90 degrees, or a disc or something like that, depending on how big your antenna is. And what that capacitance does, again, is it takes time to charge. Once the RF gets to the end of the wire where the capacitance is, it charges that and then reflects back. And that can also delay, give you some time delay. So the total time delay from the feed point to the end and back works out, again, with a shorter antenna because of the inductance and or capacitance hat, to make the timing work and make everything be resonant. Along with that, we talked about the high current area being where the radiation occurs. If you mount an antenna down on your bumper and a vertical whip antenna working against a ground plane like your car body is just half a dipole. So all the same stuff applies. It's just occurring in half of an, half a dipole instead of a whole dipole. So if you mount your whip down in the bed of your truck or down on your bumper, the high current area near the feed point is down low and it's being blocked by your vehicle. And the tip that's up above your roof line really isn't doing anything as far as radiation goes. So that's why you want, if you can, that's why you want your antenna on the roof. You want it up high above the roof line so that RF gets out. And 0 EMP.
Other comment? LEV? Yeah, for VHF, UHF antennas, yeah, want them as high as you can because typically, well, take the top of the Suburban. That's a very good image plane. 5/8 waves do indeed produce the rumored gain on a Suburban centered in the roof. However, what a lot of people do not realize, in an HF installation, the largest distribution of high current is going to do most of the radiating. And once you've launched the current into the screwdriver or inductively shortened whip, you're relying on, yeah, it would be an image plane, but there's far more current distributed over a much larger area. Where I'm heading is for HF, and let's forget about 10 meters and 15, 80, 40, 20. For the most part, it's the body of the vehicle that does the radiating. The screwdriver really is there to set up resonance and to launch current, but most of the radiation happens from the body of the vehicle. That's why it's so important to bond portions of the body together very well, which typically out of Detroit, that's not the way it's done. Some may even be just glued together. W0LEV.
Okay. Well, lots of good points here. Any questions from all of this? This is N7GES and the Tech Net. We're talking about why, what part of the dipole does most of the resonating, and why do they have to be as long as they are? And we've had some good simplified descriptions that may be a bit easier to understand. Questions on all of this stuff additionally? Just asking, Mark, did we answer your questions sufficiently? To cut him away from the radio. Okay. Anyway, good information. So we've talked about dipoles. Obviously, the same sort of thing applies to other antennas as well. We talked a little bit about the Moxon Would anybody like to talk about some of the other types of antennas we use and how that works out as there as well, especially with the different shapes and things that we're using here?
Just one comment here. Greg mentioned twin lead, window line, open wire, parallel line does not radiate because the fields are traveling opposite each other in the wire and the far field cancels. I like to comment the differentiation as far as analysis, equations, and so on go. The differentiation between an antenna and a feed line is an antenna, the fields open onto free space and radiate. Transmission lines, they close on themselves, therefore do not radiate. Just a very obvious distinction between antennas and transmission lines. But in a lot of cases, the equations can be the same. W0LEV. Okay, other antennas.
Anybody want to start us off? Particular antenna you might want to ask about? About the beam antenna.
Why is a typical radio astronomy antenna so huge? Never mind, I'm pulling your leg, Kevin.
Okay. What about the basic beam antenna? We have some interesting things happening there with the directors and reflectors and that sort of thing. Shall we talk about that a little bit? We have a lot of people that have checked in here, and any of you, please feel free to come in and make comments or ask questions. And if you haven't checked in, you're still very welcome to pop in and ask questions and or make comments. So please don't be shy.
The antenna is the single most important aspect of an amateur station. There must be questions.
Yeah.
CF, go.
About these dipoles and the loading coils, I've been hearing, I guess now, it kind of makes sense why you'd want loading coils near the base or near the feed point, because that's where the inductive portion needs to be. But I've also seen other places where loading coils are being placed at the end of the antenna, which doesn't make any sense to me anymore, although there are some references that that's the better place to put it. Any reasons for one or the other?
There are better places to put it, but realizing as you move up the structure away from the feed point, you're becoming less inductive and more capacitive. As you move farther away from the feed point, you require more and more inductance for the same resonant frequency. Indeed, you do increase the efficiency of the radiator, but at the expense of more inductance. And realize the feed inductance or radiation feed resistance or radiation resistance of these antennas, shortened antennas, is very low. Some of them, especially on 75 and, heaven forbid, 160, the resistive losses become dominant over, the resistive component of the system becomes greater than the radiation resistance. So inefficiency is sacrificed. Yeah, moving up the structure will render a more efficient radiator. Problem is, it does require more and more inductance as you get toward the end. W0LEV.
Okay, good question. Does that help with the explanation, Ben?
Yeah, sure does. Forgotten about the fact that, yeah, the resistance of the loading coil does hurt, but yeah, it makes a lot less wire necessary to keep, wires and the amount of wire that's part of the coil to make it resonant.
Okay, very good. Thank you. Other questions?
KB0SCX.
Good evening, George. Go ahead.
Can we talk about polarization for a minute? I understand that if your arms of your dipole are going out to the sides, you have horizontal polarization, and if you turn your dipole up and down, you have vertical polarization. And what the heck is circular polarization?
Circular polarization is where you have equal energy in both the vertical and horizontal components of the electric field vector. And then there's RCP, right hand and left hand circular polarized. Matters which way you, typically to drive a screw in, you turn it clockwise if the threads are cut right. To unscrew it, you turn it counterclockwise. Same with right RCP and LCP, right-hand circular polarization, the left-hand circular polarization. However, each case, there's equal energy in both the vertical and horizontal components of the propagating wave.
Okay, George, does that help, or do you need more info on that?
Well, that helps, but I'm wondering what the advantage of using circular polarization is. I see it referenced to satellites a lot.
Most times satellites, well, sometimes satellites are what we call spin stabilized. That is, we establish an axis of rotation which stabilizes the satellite to tumbling. As such, we need antennas that won't go through nulls every 90 degrees. So we use circular polarization.
Okay, thanks. KB0SCX.
All right, George, very good. We had a double with you. Who was the other station?
MIC.
MIC, go ahead.
W2MIC, a tiny bit of background on Dave's comment. If you have a horizontally polarized dipole and a vertically polarized dipole, there is very significant loss on the receiving end, like on the order of 22, 24, 25 decibels. Remember that 10 decibels is a factor of 10, so 20 decibels is a factor of 100. And 5 decibels is on the order of a factor of 5. So you're looking at a loss factor of about 500-fold. If you, as Dave says, have a spinning satellite, and the satellite has a straight half-wave dipole aimed at the Earth, and the satellite is spinning. And down here on Earth, you have a half-wave dipole. As that satellite rotates, keeping the orientation towards the antenna on Earth the same, the spinning dipole up on the satellite is going to go through 20 to 25 decibel signal fluctuation each time the satellite rotates. The advantage to a circularly polarized antenna on the satellite and on the ground is, as the satellite rotates, there is no changing of horizontal versus vertical polarization, and there is no dropout and no swing in signal strength.
Okay. Thank you very much. The extra clarification sometimes is very, very helpful. Very good. Others, please? Questions, answers, comments? This is N7GES in the Tech Net.
Yeah, Kevin, let me dispel one very common myth about vertical-horizontal polarization versus frequency.
Okay, go ahead.
Yeah, for VHF, UHF, line of sight, so on and so forth, ideally, yeah, you'll see a very, very deep null when you're cross-polarized, as Mark commented. However, everything and anything off the ionosphere, that is HF, you can go up vertical, you're likely to come down horizontal. It will be circularly polarized, I should say elliptically polarized. Circle being the degenerate ellipse where the major and minor axes are identical. Often thought, and I hear it all the time on HF, well, I'm vertical and you're horizontal, that's why I can't copy. Wrong answer, wrong theory. Anything off the ionosphere will be elliptically polarized. It doesn't matter whether you go up vertical or horizontal. It will come down or refract with some vertical and some horizontal component. W0LEV, that's HF.
Okay. Right, thank you very much. Okay, other antennas? First, other questions or comments? So since we're talking circular antennas, how do we make the circular polarization happen? What physical requirements do we need to make that happen? Is that something that's fairly easy to explain?
EMP.
Okay, EMP.
You take two dipoles, one horizontal and one vertical. You can put them together so that the feed points are next to each other and feed them a quarter wave out of phase. So the feed line going to one is a quarter wave longer than the feed line going to the other one. And because of the phase difference, you get two different waves that are quarter wave out of step, and it rotates. The other way to do it is to take the same two dipoles, feed them in phase together, but move one forward a quarter wave distant from the other one. That achieves the same thing. A while ago I had some questions about visualizing in my mind exactly how this works, and W2MIC found me a couple of very good YouTube videos that had graphics of how this works, and watching the graphic made it clear in my mind, but I can't explain it with just words. He might know what link he sent me, and he might be able to put it out here, or we might be able to attach it to the YouTube thing at some point, but that's the gist of it. The other way is with a spiral antenna, a coil antenna, a helix fed at the base, and it's one turn every quarter wavelength of forward distance makes one complete turn, and yeah, that's the other way to do it. N0 EMP.
N0 WIQ.
Carrie, WIQ, go ahead.
Well, I was at a gathering of amateur radio operators one time, and one of the guys had a helical wound antenna that he'd made out of about 2-inch aluminum tubing, and he'd rolled it around so there's about a 1-foot diameter, and I think the thing was about 6 foot long, but I only saw it. I never tried to use it or anything, so I just thought I'd mention that. But anyway, antenna questions. There's almost an infinite number of antenna questions, along with about an infinite number of antenna solutions. So what can I say?
Okay, very good. And yes, I do remember now the description from my license questions about setting those kind of things up as well. That was a little on the confusing side when I studied it, I remember. So the descriptions we've had here this evening help to make that a lot clearer as well. Other comments or questions? Questions from anybody? We've covered a lot of stuff here. As Dave said, hopefully that generates some questions as you start thinking about building an antenna or changing or modifying an antenna. What sorts of questions come to your mind as we've talked about some of these things?
MIC.
MIC, go ahead, Mark.
Old business. I pulled up the email that I had sent to Greg with the pointer to the wonderful YouTube video that shows polarized waves, cross-polarized waves, and circularly polarized waves. I have forwarded a copy to Greg and to you, Kevin.
Okay, very good. Thank you, Mark. Appreciate it. And yeah, you know, things like that are always helpful when you're dealing with something like magnetic and electrical currents, which you can't see, you know, in the air. The graphics and examples and descriptions like we've had here and various things that have been created certainly are helpful to understand what's going on in those wires and in the air around those wires and in the air far from the wires when the waves have gone elsewhere. Very good, thank you. Other questions or comments? We've covered a lot of material here this evening. Hope that people have gotten some good info and some good reminders of some of the basics that we studied when we got our licenses, because that can be very, very helpful when you're trying to either diagnose an antenna problem or make your own antenna. So, very good. Let me open it up and ask if there are any other questions of any topic that anybody would like to ask before we close the net today.
CF?
Go ahead, Ben. CF?
looking at the diagram of the screwdriver antenna, and one of the things that I've always worry about, at least in any any transformer design, is that rings that are parallel with the windings are always bad, because that eats up energy that's being transmitted through these coils. And I guess maybe I haven't taken a really good look at how the connections made to the bottom half of the unused portion of the coil, in order to make sure that we don't short out the whole thing and get a ring there that will eat energy. AE0CF.
Okay, anybody want to make a comment about that?
And any shortened antenna, any resistive loss is to be avoided. Again, I think there are a number of people on this repeater who have installed screwdrivers and discovered that the bonding at the base of the screwdriver to the chassis of the vehicle, and then ultimately tying portions of the chassis together intimately at high frequency, not just DC, is extremely important. And I believe on a screwdriver, the variable tap is probably beryllium copper. That's what's typically used for low resistance contact. It's generally pretty inert as far as corrosion goes, and it maintains its springiness, so even though the coil may corrode just a bit, the springiness will cut through it. Yeah, you're absolutely right. That's extremely important, and that's why some of the screwdriver type antennas probably work better than others. And from what I've seen, you get what you pay for. And as far as close by equipment is concerned, even dielectrics at the top, remember this is a very high Q circuit. And anything, especially conducting material that gets close to it, will detune it. It's a very high Q circuit. W0LEV.
You mentioned something, Dave, about bonding at high frequency. Could you state that again for me?
I looked at one really closely to see how that works. And yeah, that there should be those contacts that wipe against the coil. I assume that there's a plastic something form that makes sure that the windings on the screwdriver doesn't short against each other, or maybe just insulation. But well, actually, it can't be insulation because you need to wipe against it. But as it enters and retracts from the tube, either there's a stub on the bottom of where it exits the tube, or it has to short all those extra windings together, which is bad. So at least from what I've been working with, and coils and stuff like that. So I don't know. AE0CF.
Yeah, I personally have never taken apart a screwdriver or other incantations thereof. I do know the better ones use beryllium copper finger stock to make contact, the tap on the coil. I don't know what the coil's wound on. I don't know if it's free. Well, it can't be free form. It's got to be supported somehow. I really don't know. Although I might comment, over and above the screwdrivers, I've been through a number of roller inductors for my HF antenna matching network. Most of them are pretty miserable. Those that have one little wheel that turn over circularly wound inductor, there's so many disconnects on that it's not even funny. I flushed those long ago. The inductor I'm using is actually gripped on both sides of rectangularly wound, inductor that's wound with rectangular silver-plated copper, and it grabs. Now, when you reverse direction, it'll let go for a very short period of time, but there's 2 grabbers and 2 friction contacts, and it's the only one I've ever found that's worth its salt, including some very expensive ones that Polestar puts out. Hang on, let me reset. To answer Kevin's question, yes, if you measure 1 or 2 or 3 ohms DC between members of the car, forget it. They're not connected RF-wise. RF continuity is measured in, embodied very, very differently than DC continuity. And if members of the car are anything more than the shorted leads of your DMM, it's not a good RF connection. I can't stress that enough. DC measurements of resistance are not adequate, do not reflect the continuity at RF frequencies. W0LEV.
Okay, thank you. Yes, and I know we've talked about that some before as well, so I just wanted to get a sufficient description there to really understand that well. All right. Okay, other questions, please.
MIC.
MIC, go ahead.
Brief filler to Dave's comment. I have been inside several screwdriver antennas. Screwdrivers are typically wound on PVC pipe or some sort of plastic rod, typically plexiglass.
Yeah, so the beryllium copper wipes on the outside of the coil.
Okay. Other comments? Questions?
DC.
DC. Good evening. Is that Rob?
Negative, Kevin. W0RDC. Now, question on these antennas. Now, we haven't necessarily talked about the gain. How do we come by that particular figure?
I need a whiteboard, and I need to communicate the unit sphere. Blow up a balloon, and you plant a little flashlight in the middle of that balloon somehow. That little, flashlight bulb. You'll find the flashlight bulb pretty much illuminates the surface of that balloon equally everywhere. That we would refer to as the unit sphere in antenna theory. If suddenly I put a lens in front of that flashlight bulb, you'll find that a portion of the balloon is lit far more than the rest of the balloon. That's gain. You've used the lens to concentrate a good portion of the energy in one direction, but at the same time you've lost energy elsewhere. It's focusing the energy. In a concept, actually it's directivity. That won't go into the fine points difference between directivity and gain, but what I've illustrated as gain, directivity.
Okay, good. That kind of goes with that. Now, is there a different way to come up? I mean, with the balloon theory and your light bulb there, that's kind of key. Now, with that in mind, is it work? Do we have higher gains? Yes, most likely, with beams than we do vertical antennas.
Yes, indeed. As a conducting image plane, it's actually lossy over dipole. But the advantage is, of course, if it's an infinite or something approaching an infinite, or you got a good radial plane laid down, it's a very low-angle radiator, even though compared to even an isotropic, which the isotropic refers to my first example of the flashlight bulb in the middle of the balloon illuminating the surface of the balloon equally everywhere. That's an isotropic radiator. A dipole will have the pretty much standard donut pattern. If it's a horizontal dipole, the donut hole will be at the feed point, and the axis of the donut will be vertical. Again, I wish I had a whiteboard. This whole discussion, Kevin, really needs a whiteboard. When you produce less gain, there's a larger area on the balloon illuminated with less energy. As the gain increases, that illuminated spot becomes smaller and brighter. It's just, I think that's a reasonable indication of directivity. Basically, the difference between, and I have to say this, sorry guys, difference is directivity is really what the radiating structure produces in directing the energy. Gain has losses taken out of that. Typically, in the amateur world, we don't include that. We just lump directivity and gain equivalent. They're really not, but for all practical purposes, in our world of amateur radio, they're equivalent.
There you go. Basically, focusing energy in one particular area of the radiation pattern. I got you there, and I appreciate it. Thanks. So we got over that pretty good, Dave. Thanks. W0RDC. Back to you, Kevin.
PRB. Who is that? PRB?
Yeah, sorry for the late check-in there, Kevin. And I was just listening to that. And Rob, you got it. It's a focus, is what it is. It's like looking through a pair of binoculars. You know, the stronger the pair, the less your field of view is going to be. So when you think about that, you're looking in one direction. You can't see to each side, so you have nulls. You have a null behind you. Of course, you can't see through the back of your head either. So if you think of a beam in that aspect, and the more elements you apply, the stronger that focus. Okay, so and the more you increase the focus or the gain, the narrower your beam is going to be as well. So you hit that right on the head when you mentioned focus. A lot of people don't relate it to that. Go ahead, Kevin.
Okay, thank you. And it sounds like you're not feeling so good. Are you fighting that cold or something?
Yes, sir. Yes, Kevin. Both Luann and I, we went to the party, Christmas party, and then another Christmas party, and well, we picked something up along the way.
Oh, it is the season, but I'm sorry to hear that. That's not good. Okay. Well, hopefully you recover quickly. Other questions or comments?
MIC.
Go ahead, MIC.
I want to layer on to Dave's and Phil's comments. There's another aspect of gain, and I'm going to talk here about a Yagi antenna, a Yagi Uda. As both Dave and Phil have alluded, the more elements you put on, the more directive it gets, and the more forward gain you get. In other words, if you point the antenna at something and you have a number of elements, you may get 10, even 12 dB of forward gain. In other words, the signal's louder on your radio. The other aspect of a Yagi that a lot of people are not aware of is that you get negative gain, or a null, to the sides of the Yagi. And this means that if you just, hypothetically, you're talking to somebody down in Brazil, so your Yagi is pointed due south, and there's some Yatsen jammer in California with his great big beam and his antenna and his 1500 watts and so on and so on, and he's way louder than the station you're trying to talk to down in Brazil. You can turn your beam a little bit so that a Yagi is not a laser beam. It's fairly broad, maybe 45 degrees, maybe 35 degrees. And so long as the station in Brazil is anywhere in that 35-degree sweep, you can turn your antenna to selectively position the California station in the deaf side of the Yagi, and you can knock him down 10 or even 20 plus dB relative to the Brazil station. So one aspect of a directional gain antenna is to point the antenna at the station you're trying to talk with. The other aspect is to use the nulls, or the drop-off in gain, to the sides of the antenna to quiet interfering stations that are preventing you from hearing the station you're trying to talk to axially on the beam.
Yeah, I'll amplify that.
Ed?
Mark brought up a very good point there, and probably the reason why a reasonable number of amateurs use a magnetic loop as a receiving antenna instead of the same antenna they use for receive and transmit. The advantage of the magnetic loop is the nulls are very sharp and very distinct. And yeah, there are some significant resistive losses with a loop, but they do make wonderful receive antennas for their nulling characteristic. And a fair number of amateurs into it in a big way use them for receive only. W0LEV.
EMP. EMP, go ahead. Here, I'll amplify on the amplified. There's a whole host of different receive antennas that have different patterns with a deep null. The idea being to point the null at something you don't want to hear. It could be another station, or it could also be noise. Maybe your next door neighbor has an arc welder or something, or a very noisy plasma TV, and you can find an antenna that has a deep null that you can point towards the noise source, because especially on HF, dropping the noise down can sometimes be just as good or even better than increasing the gain, the forward gain towards the signal you're trying to hear. It's all about signal-to-noise ratio on HF once you have an adequate antenna. So loops will have a null off to the side, like Dave said. So if the thing you don't want to hear is off 90 degrees from the thing you want to hear, a loop is a good choice. Some antennas, including the Moxon that we talked about earlier, have a real broad front forward direction, but a very deep null off the back if they're built correctly. And matter of fact, when they use a Moxon for direction finding, they direction find using the null because it's very sharp. And so if your noise is 180 degrees from the signal you want to listen to. A loop won't help you because it hears equally well in the two opposite directions. But a Moxon with a very deep null off the back, or some Yagis, because you can design a Yagi to have all sorts of different characteristics. And one thing you can optimize for is a deep null off the back. So if your noise is 180 degrees from what you want to hear, a Moxon or the proper type of Yagi can help you out a lot there. And then there's phased arrays of 2 or more antennas phased together to create a null, and that gets beyond the scope of tonight's discussion. N0 EMP.
Antennas are just plain little miracles, and it probably behooves us to do as much understanding of them as we can to make good use of them, to fix problems, to build or whatever. We can do a lot better with that understanding. Any questions or additional comments here? Okay. I think we've had a good discussion here and learned a lot, I hope, and hopefully those of you who weren't even asking questions are still picking up a lot of good info that you can use. And there's certainly plenty of other good resources out there to look at, but if this gives you an idea of where to begin looking, that's a great thing. Okay, so next week, kind of expounding on what we did, what we talked about tonight, and maybe we've somewhat already covered it, but I think we can probably talk a bit more about it, and that is, let me locate it here. Why is the antenna the most important part of the amateur radio station? A lot of that has been mentioned here in the past few weeks, but let's take a few more minutes to talk about that in a bit more detail. And then I think that will end our year, because I'm going to be off on the 23rd, I think, and the last Monday in January. So we'll get back, or last Monday in December, yeah, exactly. And then we'll get back into it in January again. So for next week, think up questions, come up with topic ideas, and we'll see what we can do to answer those things for you next week. Once again, if you have comments, suggestions, or topics for the net, email me at elmers@ncarc.net. And please do send me topic suggestions. I'm always happy to have those. It's nice to know if I'm being helpful with these nets. So do let me know those things. And if you have suggestions for topics, I'm happy to have that too. As long as this is performing a valuable function, I'm very glad to do it. 73's all, and thank you all for your participation. And we'll conclude for today, and I'll see you next week. This is N7GES 73's, and have a wonderful evening. The repeater is now open for normal use.
This presentation was brought to you by the Northern Colorado Amateur Radio Club. Thank you for watching, and don't forget to like and subscribe.